Okay, so we're going to talk about this driven RLC circuit, where the power supply is a function of time. And again, this is very typical. If you plug this into an outlet, this is what happens. Where omega is 2 pi times the frequency, which is around 50 hertz for your outlet. And this would be around 170 volts. So if you plug this into a circuit, again, right when you plug it in, you're going to get this kind of crazy behavior where there are these things called transients. But those transients will quickly die down. And we're going to settle into something like this, a current that looks like this. So again, it's easy to say that that's going to be the result. We want to actually, this would not be a difficult thing to show experimentally. There's a device called an oscilloscope where you can actually plot these. And so it'd be very easy to measure if you have the right tools. But we want to show that this is a solution to this problem. And in order to have a complete solution, we have to know what the maximum current is, and also this phase shift phi. So we know what omega is. That's given by the power supply. So we have to find, this is our goal. All right. So yeah, let's get to this then. So there's different ways of setting up the basic equation. Simplest way is to use the loop rule, which again is kind of questionable, but it gets the right result. Probably going to revise how I teach this down the road, but haven't really fully digested that part yet. Kind of recently discovered the problem with this. But anyways, we have here, if we use the loop rule, yeah, we have the power supply. The voltage across the power supply is going to be positive, assuming sine omega t is positive. And then we're going to have a voltage drop across each of these elements. Again, that's a bit of an assumption. Like the voltage drop across the inductor and the capacitor kind of depends on whether or not the current's increasing or decreasing, or how the capacitor is charged. But basically, you only write it down this way. EMF of the power supply minus voltage drop across the resistor, minus the voltage drop across the inductor, minus the voltage drop across the capacitor. That's our loop rule that adds up to 0. But I want to move all these terms to the other side. So we'll have and I'm actually going to change the order a little bit. I want to write this one first. So we have voltage across the inductor, which is L di dt, and then we'll add the voltage across the resistor, that's just IR. And then for the capacitor, that would be 1 over C times Q. Okay. Now we have two variables here, Q and I, and they are related to each other. So we can simplify this by, let me just make a little room here. Okay, so I'm going to rewrite this just because I have a feeling we're going to use a lot of board space here. So what I'm going to do, remember, I is dq dt. So we can write di dt as the second derivative of charge with respect to time. So instead of rewriting it, I'm going to save space. And to kind of make this a single line, let's do, actually, you know what? I think it might actually be easier if we just leave it like this. Yeah, let's work with this. So, because we know what we kind of, it's a differential equation. And again, a completely valid way to solve a differential equation is to just guess the result and then check it. And again, that's in general a completely valid way to solve equations. Like say you have the equation x squared equals 25. If you guess that x equals 5 is a solution, you can plug in and see if that it works. And if someone challenges you and says, well, how do you know? Like, how did you come up with that? You can say, who cares? I mean, just the fact that you can't explain why that's a solution, that doesn't mean it's questionable in any way. You know that 5 squared is 25. So this is a solution. It doesn't mean it's the only one. -5 would work as well. So yeah, the kind of guessing a solution is valid. We like to be a little more sophisticated though, and just think, you know, what do we expect to happen if we have this power supply that is alternating? And so we would, you know, it's not unreasonable to think that a sine function would be a solution. So usually you want to be guided by the kind of the actual physical situation. Try to guess what a solution would look like based on physical principles. And then we can check it, and if it works, great, we've solved our equation. And then there's a whole subject of differential equations where you can go and question that solution further. Like, is this the only solution? Or, you know, things like that. Are there other solutions? But here, let's just, we're going to state that that is a solution to this equation so we can work with it. And so, hopefully I can fit this in one line. So on the left side, we have this here. I'm just going to move this over so we have room to write. So if we take the derivative here, we have IM. And derivative of sine is cosine. When we apply the chain rule, we're going to bring out an omega. Definitely not going to fit this in one line. So let's then, the next term is Ri. So we have R times I. Now, what about Q? So remember, I is dq dt. So Q is the integral of I dt. So let's plug that in. We can take the constant out. So we're integrating sine omega t minus 5. The integral of sine is minus cosine. And this was dt. And so in order to make a U-substitution, let's do this. So we multiply and divide by omega. So if you multiply and divide by the same thing, you're not changing it. And now we can just make a simple U-substitution. U is omega t minus 5. Then this part becomes du. So we have sine of u du, which is minus cosine of u. Then we just plug that u back in. So we have 1 over c times q. So that'd be minus im over omega c times cosine omega t minus 5. So we started out with our loop rule, or we can just apply Faraday's law and get this. And then we plugged in, you know, our solution, which we are proposing, We haven't shown that this actually works, but you know, spoiler alert, it will work. Our goal is to find I and phi, the IM and phi. But I want to make some room here. Okay, so we can simplify this a little bit, not too much, but remember last time we talked about reactance. So the inductive reactance is omega L, and the capacitive reactance is 1 over omega C. And so we can simplify this equation. On the left side, we have this. The right side is all of that, all 3 lines. Notice that each one has a peak current in it. So let's divide that. Let's divide both sides there. All right, so on the left side, we have EM over IM because we divided that both sides by that, sine omega t. And now in this first term, when we got rid of the IM, here we have omega L. That's the reactive capacitance. And then cosine. So I am worried about board space here. So I'm kind of going to combine steps. Let me write down a few trig identities. Because we'll be using those. So yeah, sine of A plus B is sine A cosine B plus cosine A sine B, and cosine of A plus B is equal cosine A cosine B minus sine A sine B. Okay, so we're going to use these because we have cosine, say, A minus B, and sine A minus B. Actually, I'm not going to do that yet, though. I'm going to be efficient here because I have a small board. So let's just do this. It'll actually be a little shorter doing it this way. Just realize both of these terms have a cosine omega t minus phi. So we can factor that and combine them. That'll save some writing down the road. So here we have plus. Now, okay, so we took the second term. Now this first term, we have omega L, which is xi L, the capacitive reactance, times cosine omega t, and 1 over omega c, that's a capacitive reactance. So we have a minus sign in front, so we can write it like this. Okay. And so now we want to apply these trig identities and kind of clean this up a little bit. So first off, we have sine omega t. Now, here we have cosine of minus phi, which is cosine phi. Cosine of negative x is cosine of x. So we can ignore the minus sign there. And then we have plus cosine omega t. And then sine of minus phi. So we do get a minus sign there. So actually, I'm going to have to do what I did before. And I want to fit this all in one line. So let me just move the equal sign over. Okay, so that's the start of it. That's this term where we expanded using that trig identity. And now for this one, we'll use our other trig identity where we have cosine omega t, cosine phi. And then these terms are minus sine A sine B. When we take the sine of minus phi, we'll pull it a negative. So this will be plus sine omega t sine phi. And on the left side, we have this, which can't really fit here. But I want to write down one more line, and hopefully this will be clear what we're doing. So what I'm going to do is I'm going to take this whole thing and factor out a sine omega t. So here we have a term with sine omega t, where we have an r cosine phi. We ignore that term for now because that doesn't have sine omega t. Here's a sine omega t. So we have xi L minus I C sine omega t sine of phi. Okay, so we took care of the terms involving sine omega t. Now let's do the same with cosine omega t. So that term we're going to take care of. Here we have a cosine omega t times minus r sine of phi. And this term has a cosine omega t. So all we did is rewrite things algebraically. I'm actually going to try to fit this term on the left as well, just so we can see the whole equation. So we have this constant times sine omega t is equal to sine omega t times this thing in brackets plus cosine omega t times that thing in brackets. Now, in order to make these equal to each other, this here has to equal the peak voltage over the peak current, and this part in brackets has to equal 0. So like if this whole thing is equal to epsilon m over Im, if this is 0, we can ignore that term. And then if this is epsilon m over Im, then the equation matches. So we have two equations here. I am out of room, so I'm going to have to erase what we've done previously. But what we did by starting out with this equation and guessing our solution, we're able to get these two equations now. So let me write those down. We have r cosine phi plus xi L minus xi C sine of phi. That's equal to peak EMF over the peak voltage. Okay, so that's this one, and this other one minus r sine of phi plus xi L minus xi C cosine of phi equals 0. So now that that's there, I'm going to erase everything. This is what we need to finish. Like our goal now is to find phi and Im. And so we're going to use these two equations to get there. All right, so let's start with this second equation. We can say r sine of phi equals xi L minus xi C cosine phi. Just by like moving that term to the other side to make it positive. And then if we divide by cosine of phi, sine over cosine is tangent. So tangent of phi and then we divide by r. So tangent of phi is L minus IC over r. Now, remember we talked about reactance? These both have units of ohms. We can show that, like this is a Henry per second. Using our unit conversion factors, we can say that's an ohm. The other one is a second over a farad, same thing. You can just multiply by the right conversion factors and see that those both have resistance of ohms, just like the denominator. And so, well, again, we wanted phi, so we've got that because we're assuming, if we know the angular frequency of a power and we're given these circuit elements, then we can calculate all of these, and tangent of phi is a number. And we can just take the inverse tangent. So we're done with that. So now we have to find the peak current. And what I'm going to do is draw a triangle. Let's say that angle is phi. So tangent of phi is opposite over adjacent. So we can say xi L minus xi C over r. So tangent of phi is equal to that. And the hypotenuse is that squared plus that squared. Add them up and take the square root. I'm going to call that z. So just from the Pythagoras theorem, we have z squared is equal to all of that. So now let's look at this top equation here. We use the second equation to get phi. Now let's look at the top equation. So we have the EMF over the current. So that's equal to r cosine phi. Well, cosine of phi is r over z. And then we have xi L minus xi C times sine of phi, which is that. So this is r cosine phi plus that xi L minus xi C times sine of phi. And now we're practically done. So this is r squared. Both of these have a common denominator of z. So xi squared plus xi L minus xi C squared divided by z. And this is z squared on top. So we have z squared divided by z, or just z. So if we solve for the peak current, then we have the peak EMF over z, and now we're done. We can write it more completely like this. Like pretty much in terms of what we were given. So this is the solution, or I should say this is a solution. A more complete, like full solution would include these transients and be really complicated and no one really care too much about it. But yeah, so we found phi, which would be the inverse tangent of this, and the peak current, all in terms of the things that are just given in the problem. Like, I mean, in order to describe the current in the circuit, obviously we would need to know the voltage, the peak voltage, and the angular frequency of the power source. If we don't know the power source, we can't describe what's happened. And similarly, if we don't know these circuit elements, how are we supposed to predict what the current's going to do? So we assume that we're given these things: the peak voltage, the angular frequency, and RL and C. And our solution contains, like we have to check xi L and xi C. We have omega L and C, so we can find those. And here, peak voltage, we have all of our given values. And so we found a solution to our problem. And I'm going to write this down. Now, this Z, this is called the impedance. And in a sense, it acts like Ohm's law. If we look at this equation, so in a sense, it does act like Ohm's law, like V equals IR. Impedance has units of ohms. It kind of acts like a resistance, but we're dealing with alternating current, so we can't overstate it. Because in a purely resistive circuit, the current and the power supply are in phase, where here the two are out of phase by that amount phi. And so we can't say this. I'm going to write this in red because this is nonsense. Generally, for an alternating current, that is not true. But very often, we don't really care. A lot of times, we just want to look at the peak value. Again, it's going through 50 cycles per second is fairly typical. So again, trying to describe the time behavior, very often we don't care about that. But we can see, like, Z is a constant. It depends on R, L, and C, and also the angular frequency, which is kind of interesting because this impedance acts like a resistance for the circuit. And you can see it depends on the frequency. So we'll talk about that some more. But again, just to be extra clear, this is not true. It only applies to peak values or RMS values, because we can divide both sides by the square root of 2 to get the RMS values. So in a sense, it does act like Ohm's law, but only when we're talking about averages or peak values. So I've got to write this down as well. So let's write down, I think that's everything we need. And then I'm going to erase the board. All right, so any questions on this? So we have like a series RLC circuit, and now we know the current is a function of time. I'm going to write that down as well. Okay. So any questions before I erase this? All right. We're going to do a problem involving an RLC circuit. And just look one up. One thing I'll say, this phi here, let's plot the tangent function. Remember, we're taking inverses. So this is minus pi over 2, pi over 2. And again, when you're talking about inverting a function, you have to, well, not always, but very often you'll have to restrict the domain so that the function is 1-to-1. That you can't have something like this and take the inverse, because that means there's two x values that give you the same y value. So if, let's say this is a function, and I said, like y equals f of x. So if I give you x, you know what y is. If I give you this value of x, y is right there. If I give you this value of x, you get the same y value, but who cares? But you can't really go backwards in a non-ambiguous way, because if I give you this y value, do you know what x is? No, you don't. It could be either one of these two. And so to define an inverse, we have to restrict the domain so things like this don't happen. So for tangent, it's between minus pi over 2 and pi over 2. And so when we take the inverse tangent, we'll get an answer in this range from minus pi over 2 to pi over 2. So this constant could be negative or positive. So it's possible, like, it depends on what type, it depends on the details of the circuit, but generally the current and the power supply voltage are not going to be in phase with each other. And, it's like, which one is like the current leading the voltage, or is the voltage leading the current? That depends on the sign of phi. So, I just want to point out that it could take on positive or negative values. So I'm going to write, just to make this kind of more digestible pieces. We're going to stop the recording here, and then just so you can have a separate video for the problem.